All right, so this will be the methods part of the lecture, where we'll go into some of the more details of the implementation of the RNN. And then Brandon will be walking you all through an implementation in PyTorch, and you all will implement the forward pass and the training and the contextual dependent integration task, the Monte Cecilio task that we talked about earlier. So the Monte Cecilio paper uses this recurrent neural network called the continuous time recurrent neural network. So I've showed the equation before, but this time we'll actually go into the details. So this is the equation of the continuous time recurrent neural network. So the inputs are U of t. And so U of t represents the RNN input at time t. And for the Monte Cecilio task, there were the context and motion coherence inputs, as well as the which context you're in, of which there were 2. And so in that task, this is going to be a vector that is 4-dimensional. And so that corresponds to this U of t. And it's mapped onto the RNN states x of t through wn. So then x of t is what these orange dots represent. So x of t is going to be the RNN state, but there's a subtle distinction here. So the RNN state has, there's an activation that's before and after the nonlinearity. And so the x of t is called the pre-activation activity of the neural network. And this is a vector that has the same dimensionality as the number of artificial units we have. So let's say we had a 100-unit neural network. This would be a vector in R100. And you can see we have this equation here, h of t equals f of xt. So this h of t is the nonlinearity, like a tan h or a ReLU applied to x of t. And so this is sometimes called the hidden states, and h of t will have the same dimensionality as x of t. So h of t also is in R100, and it's the hidden state of the neuron. And usually when we compare the artificial activity of the recurrent neural networks to neurophysiological activity, we're doing that comparison of ht, the hidden state, so after the nonlinearity, all right? After that, when we look at the equation for our neural network, our continuous time RNN right here, then we have parameters of the network. So our parameters are the things that we get to learn and set to make the network as good as possible, to do the context-dependent integration task as well as possible. So the first one is Wn. So Wn, for the values that we've set so far, is going to be a 100 by 4 matrix that maps the inputs onto the pre-activation activity of all of the hidden artificial neurons. So Wn maps U of t onto the artificial neurons. We have a W recurrent, and this W recurrent is then what implements the dynamics of the RNN. It's going to be R100 by 100, because as you can see, it's going to map the hidden states, f of xt, onto the derivative of the state, which again tells us where we're going. So because the output is going to be 100D and its input is 100D, then WREC is a 100 by 100 matrix here. And so you can think of WREC as the matrix containing all of the weights in between my 100 recurrent, my 100 artificial neurons. And then lastly, we have a WOut. And so WOut is a readout of the artificial neural activity. Here we've written it as a WOut times f of xt. You may sometimes see it, and I think that in the code that we prepared, there's no f here. It's just an WOut times x of t. Oftentimes in convolutional neural networks, the output layer is just linear, and so it's a linear classifier at the output. If there's no f here, there's analogous linear mapping at the output of the neural network. And so z of t is going to be the task output. In the case of the Monte Cecilio task, is going to be the decision whether the neural network will go to choice 1 or choice 2. And so z of t is in this case going to be just a scalar, and therefore W out is going to be this 1 by 100 vector. All right, any questions on any of the terms within the neural network? Yeah.
Why is there a first term of minus x?
Perfect. Yeah, the question is, why is there this term minus xt? Because if you've seen recurrent neural networks in machine learning, there isn't this minus xt. So actually, to answer your question, I'm going to go to the next slide where we're going to do an Euler expansion. And what you'll see is that this xt is essentially like a low-pass filter term where you remember part of your past state. But let me go ahead and derive this so that it's more clear, and then let me know if it's still mysterious after that. So we have this equation for the continuous time RNN. And typically, when we are then coding something in Python, it's more straightforward to have a relationship between x of t and x of t plus 1, because we might implement this in a for loop, and we want to know what the next state is given the current state. So what we're going to do is we're going to do the Euler expansion of this continuous time recurrent neural network. And we're just going to use the first order approximation of the derivative. And that is that the derivative x dot t, right? This is equal to dx dt, a change in x over a change in time. And so we'll just approximate that as x of t plus 1 minus x of t. And that will be over a delta t. So actually, this should be x of t plus delta t minus x of t over delta t. But I'm just going to call it x of t plus 1 for the sake of simplicity. So if I plug this into this equation, that will give me tau times x of t plus 1 minus x of t divided by delta t. So now here you could think of t as a discrete variable, and it increments by one time step, and the length of that time step, that bin, is given by delta t. All right, so all I've done is plugged in x dot t equals this, and this is equal to minus x of t plus w recurrent f of xt plus w in u of t plus some bias b. What I'm going to then do is I'm just going to rearrange terms. So I have x of t plus 1 on the left and x of t on the right. So what I'm going to do is I'm going to write this as x of t plus 1 minus x of t. And then I'm going to define an expression for, I'm going to define alpha equals delta t over tau. Yeah, sorry. Let me write bigger in general. I just noticed how small everything is. Let me see if I can expand this. Resize. Is that better? Yeah, feel free to let me know. I'll try to use a thicker pen also. So here we have x of t plus 1 minus x of t. And then I defined alpha equals delta t over tau. So I can multiply both sides by alpha, and that'll give me an alpha times this expression over here. And then I'm going to move x of t to the other side. And therefore, we'll see that this simplifies to x of t plus 1 equals, again, if it's too small, just let me know, equals 1 minus alpha x of t plus alpha w recurrent f of xt plus w in ut plus the bias b. All right, any questions on any part so far? Yeah.
Sorry, maybe I wasn't. What is tau?
The question is, what is tau? So when we look at this equation here, we can see that tau is called the time constant of the network. It tells me essentially how long my activity will just persist irrespective of, say, inputs. So if tau was very large, let's say tau is equal to 100 milliseconds, then alpha would be very small. And if alpha is small, then x of t plus 1 is largely equal to x of t. And you have very little contribution from the actual recurrent connections to the network. So tau being longer means I remember my prior activity more strongly. Let me know if you want me to explain that again. But yeah.
No.
Okay, great. Yeah, and then back there.
My question is that I may also like to do something. So what does this like explain James' question, like why
Yeah.
there's like minus
Great. Yeah. So you can see that what this minus xt did is it ultimately contributed to this 1 minus alpha xt term. And so if you have just an expression like tau x dot t equals minus xt, the solution to this is an exponential. That's another way of saying it's a low pass filter. And so when you have this relationship, essentially there's going to be some remembrance of your past state, your past value. Your past value is going to persist through the network. Okay, let me try to say it another way. If I did not have this minus x of t term here, then this would be an x of t plus 1 equals, so there wouldn't be a minus alpha here. It would just be x of t plus alpha times this expression. The fact that there's a minus here means that there will be an eventual decay slowly of the present pre-activation states over time. And so it'll decay slowly. That's what I mean by like the low pass filter. So it has a low frequency, but eventually it will decay away. And the decay will be exponential.
So does the alpha have to be larger than 1 for you to do that?
Great. The question is, does the alpha have to be larger than 1 for me to do this? No, in general, alpha will be less than 1. It'll be between 0 and 1 typically. So usually, like let's say the time constant of the network is 100 milliseconds, so tau equals 100 milliseconds. I wouldn't want to choose delta t to be bigger than 100 milliseconds because then my step size to evaluate the next value of x of t would skip over interesting dynamics. So typically delta t is chosen to be equal to or less than tau. So you all may have heard of a vanilla recurrent neural network from machine learning. That vanilla recurrent neural network has this equation. It's h of t plus 1. And remember, h of t is equal to f of xt. Apologize, I'm writing all over the board just because of space reasons. So the vanilla recurrent neural network is h of t plus 1 equals f of w recurrent times h of t plus wn times u of t plus bias. And the way that this continuous time RNN relates to the vanilla recurrent neural network is a vanilla recurrent neural network is this equation with alpha set to 1. Right? So if alpha is set equal to 1, then this term goes away, and we are left with, let me just add another page. When alpha is equal to 1, we have the left-hand side x of t plus 1, and then because alpha is equal to 1, this term will disappear, and I'm just going to be left with this term on the right-hand side. And so if alpha equals 1, we're going to get x of t plus 1 equals w recurrent times f of xt plus wn ut plus my biases. And then if I wrap an f around both sides of this equation, so if I put an f on both sides of this equation, then this becomes f of xt plus 1 is the hidden state h of t plus 1 equals f of w recurrent. F of xt is h of t plus wn ut plus b. So this is, if you talk to a machine learning person, you ask them to do a vanilla RNN, this is the equation they'll have in mind and the way that it relates to our continuous time RNN. It's just a setting where delta t is equal to tau. All right, any questions on any part of that? Okay, so actually, that's all you need to know to do the training of the recurrent neural network on the task. The reason why is the following. Actually, there's one more thing that you need to know. In general, when we train a machine learning model, and by the way, if this overlaps with things that Chaith and Eva and others have already covered, feel free to let me know, and then I can gloss over those details. Okay, I'm told repetition is good, so we'll do it again. We need to know how good our model is doing, right? To know how to make my weights different to improve the model, I have to have a measure of how the model is doing. So that's a loss function L. And L, in the supervised case, is going to take the actual labels from the data, our supervised training set. So I'll call the labels y of t. And it's then going to compare them to what my RNN outputs. And you'll recall the RNN output is z of t. So the loss function is a function of my target labels, or my target labels and my output. And an example of what a loss might look like is it could be going across all time t, and then just record and measuring the squared loss. So how close does z of t come to producing y of t? And if z of t doesn't produce the labels well, then my loss is high, and I want to change the weights to make that loss as small as possible. This is the loss that Monte and Cicillo use, except evaluating it across all time. They only evaluate it at the first time point and the last time point. And Brandon's notebook will go over that. So that's what our loss function is. After we know how to evaluate our model, we need to then have a learning algorithm. In this case, it's going to be something called gradient descent that can change our weights to make the loss function as small as possible, or to make it smaller and smaller. And the way we do that in stochastic gradient descent is we're going to have an update rule that says my current recurrent weights, wrec, are going to be updated in the direction of the negative gradient of the loss function with respect to those weights. So basically what I'm saying is I want to make this loss function as small as possible. So I'm going to take the gradient that tells me the direction to step in to change wrec to make L smaller and smaller. All right. And then really the key challenge then is to say, how do I calculate these gradients? Because these gradients tell me the way that I change wrec to make my loss smaller and smaller. Are there any questions there? All right, again, hopefully repetition. So when you're doing this in PyTorch or in the notebook that we're going to show you, in general, calculating the gradients can be quite involved. And so in the deep learning class I teach at UCLA, we make the students implement backpropagation in one homework assignment just so that they understand what's underneath the hood. But then later on, when they're implementing neural networks, we give them PyTorch and TensorFlow, because in PyTorch, after you define the forward pass, which is what we derived over here, the way to go from inputs to outputs, PyTorch will keep that forward pass. It'll represent it as a computational graph. And it has a function called dot backward, which takes the gradient of anything in that forward pass with respect to the loss that you want to. So PyTorch really simplifies our lives by giving us the gradients of the loss with respect to any node in our network. So that's why, as long as you know the forward pass, you can actually already do all the PyTorch training. That said, even though you can do that, I'm still going to talk a bit about backpropagation and the practical challenges of training a recurrent neural network. But actually, at this point, you have what you need to know to implement the recurrent neural network as in the notebook, and Brandon will walk you guys through that. Okay. Any questions there? All right, so let me talk a bit then about backpropagation. Can you raise your hand if you've had backprop before? Okay, cool. So
where you have
Okay, I'll just do a tiny bit of repetition there.
I think you should, because I don't think we really went into the math of it. So
Okay.
what we've done, you will do it much more thoroughly.
Great. So again, you have what you need because PyTorch is going to take the gradients for us, that's loss.backward, and optimizer.step is going to do this gradient descent for us. But there are practical considerations in how we actually train recurrent neural networks. And I want to be able to at least try to distill that intuitively to you guys. So let's start with what backprop is and how it works. And then I'll show you how we do backpropagation in a neural network. So I'll just do the very simplest examples to show that backprop is just an application of the chain rule for calculus. So let's say that I had the operation where I'm going to take A and B and add it to produce C, all right? And then C is going to go through some function that calculates my loss L. L tells me how good my model is. And when I do gradient descent, I need to calculate the derivative of L with respect to my parameters. So I need to know how to take the derivative of L with respect to C. That's easy because C is connected directly to L. So I can compute DLDC, and let's say that it has some value like 5. So backpropagation is then the action of taking DLDC and then pushing it through upstream nodes to calculate DLDA and DLDB. All right. Forward propagation is the act of computing the forward computation. So forward propagation would be C equals A plus B. And then backwards propagation would be take DLDC and compute DLDA and DLDB. Right? How do we do that? It's via the application of the chain rule. So if I want to backpropagate from DLDC to DLDA, so if I want to calculate the gradient at this node, which we'll call DLDA, what I need to be able to do is I need to calculate DL, DC, and then I need to multiply it by DC, DA, right? And together, when I multiply these two together, the DC's cancel and I get DL, DA. In this case, C equals A plus B, and so if I take DC, DA, that equals 1, and similarly, DC, DB equals 1. So what that tells me is if I have an operation that's a plus sign, DLDA is going to be equal to DCDA, which is 1, times DLDC. So when I backpropagate through a plus sign, the gradient just passes through, meaning that the gradient at this point, DLDA, is also just equal to 5 because it's equal to DLDC. And similarly, DLDB is going to be equal to 5. Any questions there? So I'll do one more example.
Let me actually ask you a question. Someone tell me what DCDA is. Like, it's the derivative of what with respect to what? Come on. When you know this. Did you guys see what's happening? Can someone explain it to me? All right, you've nodded yes, so I'll have you explain.
We already know the rate of change of the loss with respect to C1 know the previous neurons. So we find with the chain rule we can use the current neuron, and we know how the current neuron changed with respect to the previous neurons, so we can put the chain rule together and know how the loss changed with the previous neuron.
Yeah. And then in this case, like Sabera was asking, DCDA is equal to 1. Ultimately, what the derivative tells us is if I wiggle A a bit, how much is that going to wiggle C? And because C equals A plus B, if I wiggle A by 0.1, I should expect C to also wiggle by 0.1. And so it makes sense that DCDA is equal to 1. All right. let me add one more slide. I'm going to do one more scalar example, and then I'll tell you what the answer is for the neural network. So if you have now A and B, and instead of being added together, they're multiplied together, and that gives C, and that goes into something that computes my loss function, L. And again, I know dl, dc. The forward pass here is to compute C equals A times B. And now if I want to backpropagate to dl/dA, what I need to do is I need to multiply dl/dc by dc/dA. And in this case, dc/dA is just equal to B. And similarly, dc/dB is equal to A. If I just differentiate C equals A times B. And so what that tells me is if I want the gradient over here, what I'm going to do is I'm going to take dl/dc, and I'm going to multiply it by dc/dA, which is B. Right? So the gradient here is going to be B times dl/dc, and the gradient over here is going to be A times dl/dc. So when you backpropagate a gradient through a multiplication, what happens is that if it backpropagates to A, I need to multiply the gradient by the value of the wire on the other side. So the gradient here gets multiplied by B, and the gradient over here gets multiplied by A. Any questions on those operations? All right, so then that's actually, I think, sufficient for us to then understand what's happening in a recurrent neural network. So when we have a feed-forward neural network, what these computations are doing is they're calculating a function. So if I call these nodes, this node over here, if I call this H2, this is going to be my nonlinear activation function times W. Let me call the weights here W2, and I'll call these nodes W1. It's going to be H2 equals F of W2, H1. And W2 times H1 is a multiplication. So I could write this as a graph that looks like the following. I have W2, and it multiplies H1, and that gives me an H2. And eventually, this thing is connected to something that calculates my loss function L. And I'm eventually going to have a gradient dl dH2. And that's the gradient at this point. And I want to backpropagate it to W2. So I know how to change W2 to make the loss smaller. And I also want to backpropagate it to H1 so that I can also eventually compute a backpropagation of dl dH1 to get the gradient with respect to W1, for example, to get the gradients with respect to all the weights in the network. All right, does that make sense? All right, so what's the gradient here? It's very analogous to the scalar situation where when you backpropagate through a multiplication, you multiply by the value on the other wire. Because these are now matrices and vectors, there's transposes to be aware of. And actually, the more formal derivation involves a 3D tensor, but the intuition is sufficient also. So if I want to backpropagate to dl dH1, I would take dl dH2, and I would multiply it by the value on the other wire, which is W2. And this is actually going to be W2 transpose. Okay. And again, this is just the multivariate generalization of this rule that we did here. If I backpropagate to W2, let me do this one in a different color. The derivative here is going to be dl dH2 times the value on the other wire, in this case H1, and it's going to be H1 transpose. Okay.
Could you maybe comment, Jonathan, on how like activation functions are not only like where they are in your image and like where they are kind of
Yeah, so Sabera is asking, can I comment on the nonlinearity? And you're going to notice that there's actually a nonlinearity here, F, that I omitted, and that's just for the sake of time and intuition, not for correctness. So there should be an F here, and if there's an F here, what we need to do is we need to multiply dl dh2 by, if I called h2 equals f of x2, then I would have a gradient dh2 dx2 that is a matrix, and I would need to multiply dh2 dx2 by dl dh2 to get dl dx2. Right? So everything is just the continual use of the chain rule here. The key take home from this slide that we'll need to know for recurrent neural networks is that when we backpropagate through a neural network layer, we are always going to get multiplications by what's on the other wire. So if I backpropagate dldh2 to h1, I'm going to have to multiply dldh2 by what's on the other wire, which is w2. Right? Any questions there? Okay, so let's then get to the recurrent neural network. So for a feed-forward neural network, it's really straightforward to backpropagate because you're just using the chain rule, and there's only one direction that you can go. The problem with the recurrent neural network is that now there are loops, right? And so there's not just one direction that you backpropagate through. You have to backpropagate in all sorts of different directions. And furthermore, the activations themselves are time dependent and also dependent on the input that changes also across time. All of these mean that it's not straightforward to just naively say, I'm going to apply the chain rule to this recurrent mess of connections. We need another way to actually do the backpropagation. So the way that we do this, and I'll explain this intuition in more detail on the next slide, is that we unroll the recurrent neural network in time. So if we were to just consider, for example, the vanilla recurrent neural network equation, that's h of t plus 1 equals f of w recurrent, h1, plus w in ut plus bias. Right? Sorry, this should be h of t, not h of 1. What this tells me is, let's say that t is equal to 1. It tells me that h2 is a function of h1. So if I look at h2, it's going to be a function of h1 plus u2, since t equals 2. So u2 and h1 combine to give me h2. And with h2 and now u3, I can calculate h3. And so now if I write the recurrent neural network, not as a network of just the neurons and their recurrent connections, but if I unravel it in time, then in time, it now becomes a feed-forward neural network. So there are no recurrence relationships here. Let me unpack that a bit further. Let's say that this was our neural network. It has 4 neurons, and W recurrent is equal to this matrix. So what this means is that if I were to go ahead, I'm just going to write over this. We know that h of t plus 1 is going to be f of W recurrent times h of t. Let's just ignore the inputs for now. Right? So if I put h of t here, so h of t is going to be a vector that is, in this case, 4-dimensional because I have 4 neurons. So I'll write h of t, 1 for the first neuron at time t, h of t2, h of t3, and h of t4. Hopefully that's still legible. All right. And I apply f to this. This is going to equal h of t plus 1, comma 1, h of t plus 1, comma 2, down to h of t plus 1, comma 4. All right. And so what that means is that if W recurrent has a 1 here, right, it says that the first neuron's activity at time t is going to be then multiplied by 1 to give me the first neuron's activity at time t plus 1. And that corresponds to this self-connection. So this value 1 corresponds to this connection here. For neuron 1 at time t plus 1, it also gets 0.4 times ht4. So this 0.4 tells me that ht, comma 4 has a weight that goes to the first unit and the value of that weight is 0.4. I'll do one more. If we look at the activity for neuron number 2, it's going to be 0.9 times the activity of neuron 1 at the prior time step, and so that's this connection. That is 0.9. There's also a 0.6 times HT3, so neuron 3 connects to neuron 2 with a weight of 0.6, and then lastly we have a 0.5 here, so that's the fourth neuron going to the second neuron with a weight of 0.5. Question?
Can the weights be negative?
The question is, can the weights be negative? Yes. Yeah, so the question is then, what does it mean? So in a recurrent neural network used for neuroscience, you could think of the y-axis as, even though the activations are, so actually usually in RNN modeling, you want to avoid negative activations. So we might use a nonlinearity like ReLU, F, for example, which is only non-negative. If we use tan H, which goes between -1 and 1, we could, for example, add 1 to it so that it is also non-negative. If the activations can go negative, then it's an even more abstract state that doesn't correspond directly to neurons or populations of neurons. So actually in Brandon's work, he used 1 plus tan H to make sure that the activations don't go negative. All right, any other questions here? Okay, so let me show you then how we unravel this in time. So if let me just copy and paste this so I don't have to draw it again. This act of unraveling in time means that we take the first neuron's activity and we write nodes for its value at time t-1, t+1, t+2, all the way up until time big T. And now every single one of these weights is going to be the same value as this weight, which tells me how neuron 1 updates itself through time. So all of these weights then become the value 1. And then neuron 4 also affects neuron 1. And so all of these weights are also the same, and the value of that connection is going to be 0.4. All right. And then similarly for neuron 2, which we did in red, there's a connection from neuron 1. That's this connection that has value 0.9. This one is also 0.9. And then I think you guys all get the picture. These are 0.6. And these are 0.5. Any questions there? So you'll notice then that this connection matrix is the same across every single point in time, and this is our matrix W recurrent. Any questions there?
Could the weights of the recurrence be time dependent?
Great. The question is, can the weights of the recurrence be time dependent? There are ways. So if you just make it W recurrent as a function of T, that will be very challenging to train. It essentially becomes a feed-forward neural network where you have different weights at each one of these connection points. And we know, at least for CNNs, it's tough to go beyond 22 layers. So if you have more than 22 time points, it's going to be difficult to train that with backpropagation through time. That said, there are other ways to make it time dependent. So there is this architecture called the multiplicative RNN. This is from Sutskever, Martins, and Hinton, I think in 2011. And what you can do is you could define WREC to be a function of the input. So it could be something like a matrix A times diag of your input times B. And this then causes WREC to be time dependent. It's a more complex architecture though.
Does the current structure look like a reduced form of feed-forward neural network?
Yeah, ultimately every recurrent neural network can be boiled down to a feed-forward neural network where the number of layers is given by the amount of time. And so I think I might have actually had a quote on a prior slide. Yeah, so Schmidhuber then views RNNs as the deepest of neural networks because their depth is however long they run for. Right. Any questions here? All right, so Brandon will go through then the details of this in PyTorch. Now, with that in mind, what we can do is, because this is now a feed-forward neural network, we can use our backpropagation rules that we discussed at a high level earlier to backpropagate the gradient and learn the derivative of the loss with respect to W recurrent. And then we can change W recurrent to make the loss smaller. What's the challenge in this? So what I've now done is I've drawn the computational graph of a recurrent neural network. And I apologize, these should be U1, U2, U3. And I've drawn it in this way to make a point, which is that, let's say I calculated the gradient over here. So let's call this, over here. Let's call this DL DH3. To backpropagate, even though this is now a feed-forward network, when I backpropagate it through this multiplication sign to get DL/DH2, I have to multiply the gradient by what's on the other wire. And what's on the other wire is WREC. So DL/DH2 is going to be DL/DH3, some function of it multiplied by WREC. And now if I backpropagate again to get DL/DH1, when I backpropagate through this multiplication, again, I have to multiply the gradient by what's on the other wire. And again, this wire is just W recurrent. In fact, it's W recurrent at every single time step. So when I backpropagate over time, this algorithm is called backpropagation through time, my gradients are going to be multiplied by W recurrent, WREC, over and over again. And this is a really big problem for the following reason. Let's say I backpropagated t time steps, lowercase t. If I backpropagate lower t time steps, I'm going to have to multiply by WREC t times. WREC will have an eigenvalue decomposition given by u, lambda u inverse. And this is raised to the t, meaning that I multiply it by itself t times. And so now this is going to equal u lambda u inverse times u lambda u inverse t times u lambda u inverse. What you'll notice is that all of these inner u inverse u's cancel out to give me identity. And this therefore simplifies to u lambda raised to the t u inverse, where lambda raised to the t, lambda is my matrix of eigenvalues, lambda 1, lambda 2, to lambda big N, where big N is my number of artificial neurons, and each of these is raised to the t. All right. So let's say that I wanted to backpropagate through 100 steps of time. This is not unheard of. If you're doing a language model, characters that were 100 characters ago, words that are 100 characters ago, can still have a meaningful impact on the text that you're generating right now. So backpropagating through t equals 100 time steps is not unheard of. The problem now is if lambda 1 is slightly bigger than 1, so maybe lambda 1 is equal to 1.1. 1.1 raised to the 100th is a big number. I wrote it down here. It's 13,780. So now our gradients, DL, DW, are going to be exploding. They're going to be huge. And if you take gradient steps that are too big, you're never going to converge. If lambda is small, lower than 1, like 0.9, 0.9 raised to the 100th is going to give you 2.7 times 10 to the minus 5. And so if your eigenvalues are less than 1, then your gradients vanish. And if you have no gradient, you're not going to change your parameters at all. So both of these cases lead to no learning. And because for recurrent neural networks, you're backpropagating through the same W recurrent over and over again, that will lead to what is called the fundamental problem of deep learning, that your gradients either explode or they vanish to zero. Right? Any questions here? Okay, so in general, how do we address this for vanilla RNNs? In general, we can truncate backpropagation through time. So if we can't go back 100 time steps, but we could go back 50 time steps, then I might just limit the backpropagation from time 100 back to time 50. And then time 99 only goes back to time 49. And then after that, I don't compute any more gradients. And so that's truncated backpropagation through time. And if you had exploding gradients, it would cause your gradients to not explode, and you might be able to do some learning. For exploding gradients, we can do something called gradient clipping. And what this does is it looks at the magnitude of my gradients, dl, dw. I'll just call that g here. And if that's bigger than some threshold c, then I'm going to scale down the gradient. So I'm going to then say that my new g is going to be my old g, but it's going to be scaled down by c over norm of g. So the biggest the gradient norm could ever be is equal to c. There are other regularizations that ML people have employed to address vanishing gradients. And just because I'm doing poorly on time again, I'm going to skip this. There are also weight initialization strategies. So something as simple as initializing W recurrent to be the identity matrix, and the identity matrix has all eigenvalues equal to 1, actually do wonders for some RNN training. Like you will train a lot faster and you'll be able to learn longer temporal dependencies. Right? And then in most machine learning applications, you actually rarely see the use of vanilla recurrent neural networks. The primary way people get around this vanishing and exploding gradient is to use a different architecture, like an LSTM. And the LSTM I'll go over next. But any questions here? Okay, so I'm going to give maybe a more whirlwind summary of the LSTM to just show you guys the intuition of how a different recurrent neural network architecture works. Okay. What's like? Actually, yeah. Okay, I'll go a bit quicker, but I'll still try to get the intuitions through. So this was developed in 1997, and it's the primary there's a closely related architecture called the GRU, are the most frequent recurrent neural network architectures you are going to see in deep learning. So this is what an LSTM is. If you're anything like me, you're going to see this and think this is totally non-intuitive. I have no idea what these equations mean. So what we're going to do is we're going to write a computational graph for this LSTM, and then I'll tell you guys the intuition of how it works. So we're going to take all of these equations, and I'm going to write this graph. So in this graph, we have first a concatenation step. So we concatenate h of t minus 1 and x of t. That gives me all of these bracketed terms where h of t minus 1 and x of t are concatenated together. And then when I write the sigmoid here, this is the sigmoid function. The sigmoid function looks like this. I'm sure you all have seen it before, where on the x-axis is the input, x. The y-axis is sigma of x. And it goes from 0 to 1. And at x equals 0, the value of the sigmoid is 0.5. Okay. So when I then want to draw what f of t is going to be this line over here. It's going to be a sigmoid applied to wf times this concatenated h of t minus 1 and x of t and a b of f. So I've taken away the wf and the b of f, but it's going to be encapsulated in the sigma just to make this diagram as simple as possible. All right, so this is f of t. I of t is going to be this line right here. This is I of t, so that's this sigmoid. This v of t, which goes through a tan h, is going to be this right here. Tan h is just it goes from, it's like a sigmoid, but it goes from -1 to 1. And I'm sure some of you are already thinking, why are there sometimes sigmoids and sometimes there's tanh, and I'll explain that. And then there's going to be an O of t, which is a sigmoid applied to this affine transformation. That's this node right here. And then our next hidden state, h of t from h of t minus 1, is going to be O of t times tan h applied to c of t. And so that's this operation over here that then gives me h of t. All right, so this is just the block diagram of the LSTM. Any questions here?
Just for clarification,
Yeah.
the XT should be the input, right?
Yes, thank you. Yeah, so for all of these slides, U of t has now become x of t. Sorry for that inconsistent notation. These ones I copy and pasted from my machine learning class, so that's why they're a bit different. Okay, so the key thing that the LSTM introduces is this cell state that is called C of t. And introducing the cell state, we're going to see, really helps us with exploding and vanishing gradients. We'll see why that is in just a bit. But let's first look at the cell state and the operations that it does. So when you think of the cell state C of t, the top line of the LSTM, you should think of this as a memory or a tape. And so for a memory, there are 3 things that we can do to it. We could forget what's in our memory. We could write in new information to our memory. And then we could read out the information from the memory. And each of these 3 operations is done in one time step for the LSTM and occurs through these 3 operations. All right, and so this is where I'm going to accelerate a bit more, since I also want to talk about fixed points at the very end. So f of t is called the forget gate. And if we look at the equation for f of t, we see that it's a sigmoid applied to this affine transformation. A sigmoid is something that goes between 0 and 1. And so f of t is going to take on some value between 0 and 1. And if f of t is equal to 1, then I keep all of the memory in my cell state because c of t minus 1 then multiplies 1, and therefore at this wire here, I still have everything in my cell state. If f of t is equal to 0, that tells me to forget all of the information because c of t minus 1 then goes to 0. Okay? So the forget gate is this multiplicative factor that tells me whether to keep or forget information. The write-in information happens with these 2 gates. We'll call this I of t the input gate and v of t the value gate. So I of t is also between 0 and 1. And I of t tells me how much of this value v of t to write in. All right, so at every single time step, the LSTM is going to compute some value to write in, and values are things that go through tanh. So it can go between -1 and 1. So it'll always calculate a candidate value to write into the cell state, but whether that value actually gets written in is going to be mediated by the input gate. So if the input gate is equal to 1, then you write in all the information, and if it's 0, you write in 0 information. Right? And then lastly, we have a readout. So that's applying tanh, which calculates a value from the cell state. And then the output gate, O of t, is a gate that tells me how much of my cell state I want to read out to the hidden state. So O of t is also through a sigmoid. It's also between 0 and 1. And so if O of t is equal to 0, then I'm not going to read out any information, and my hidden state will be 0. Whereas if O of t is equal to 1, I'm going to read out all the information from my cell state. All right. Any questions there? Great. The question is, why is it sometimes sigmoid and why is it sometimes tanh? So whenever there's a value, we use a tanh. That's kind of like how in a vanilla recurrent neural network, f might be a tanh. So the tanh will spit out like the rates of the network. And all of the sigmoids correspond to the gates that either tell me to forget information on a scale from 0, forget everything, to 1, forget nothing. I of t is from 0 to 1, where 0 is don't write in information and 1 is write it all in. And O of t is 0 to 1, 0 being don't read out information, 1 being read it all out. Great question. Anything else here? Sorry, can you repeat that, Sabera? Yeah, perfect. Yeah. So if I call this whole thing, sorry, let me do it like this. So this whole thing I could call a function LSTM. And what LSTM then does is it takes LSTM applied to h of t minus 1, and my input x of t will give me my new state at ht plus at h of t. And then I could wrap LSTM of h of t and then x of t plus 1 to get my next hidden state h of t plus 1. So this is just it for one time step, but you would run this over time as well. Okay, any questions there? Okay, so let me just tell you, yeah.
So I can see from the three components here, like the forget part is the long-term memory, the writing information is the short-term memory part. Is the readout affect how much the network remembers?
So the readout, because ultimately we compare to h of t, these are the rates. And so maybe one way to think about it is that there's a whole lot of information that's stored within the memory, within the cell state. But to actually perform your task, because your output is going to be a function of h of t, you want to just take out the information that you need to compute the output at that time, rather than all the information stored within the cell state.
So the cell is more like the long-term memory, the HT.
You are correct in saying that C of t, the cell state, is a long-term memory, yeah. Question?
What is H versus, what is H and what is C again? C is the cell state, H is the readout from?
Yeah, H of t are the hidden states. H of t is ultimately what we compare to neuron firing rates. And so the H of t's are used to compute the output, and their activity we compare to the firing rates. So let me just skip these slides because I gave the high-level overview of the LSTM, and tell you now why it is that the LSTM really strongly fixes the exploding and vanishing gradients problem from RNNs. When we backpropagate through this memory, we are going to have a DL dct. And the first thing that we backpropagate through is a plus sign. And you'll recall that in an earlier slide, we calculated that if you backpropagate through a plus sign, the gradient just passes through. DLDA is equal exactly to DLDC. So when I see a plus sign, the gradient is really happy because the gradient does not change at all. It backpropagates exactly past this plus sign. Now when I backpropagate from this wire to DLDCT minus 1, I need to multiply by the value on the other wire. And this other wire was the forget gate, which is between 0 and 1. But if we want to retain memory, f of t is equal to 1. And so if I backpropagate through this multiply, I multiply by the value of f of t. And if we wanted to remember something, f of t equals 1. So I backpropagate by multiplying by 1, and the gradient stays alive. So we call this a gradient highway sometimes in machine learning. It's really nice because on the cell state, the gradient doesn't decay unless you wanted to forget information. So it's actually like a feature. If f of t is 0, then I want to forget information at that point in time. And so if I want to forget information, then that information from the past shouldn't affect the future, so my gradients should go down to 0. But as long as you want to retain information, then the gradients will continue to pass back, and they won't explode or vanish. So that's the architecture of the LSTM and how it addresses this fundamental problem in training RNNs. All right, let me just do the last thing, and then I'll be happy to take questions. Sorry for being a bit over time again. The last thing is identifying fixed points in a recurrent neural network, which Brandon provided code for in the notebook. And I'll just do this fairly quickly. The fixed points are those points for which x dot t equals 0. That the flow field is 0, which means my velocity is 0. If you're at a stable fixed point, then you stay there across all time. So if I set x dot t equals 0, that's saying that now my equation becomes 0 equals minus x. And because it's a stable fixed point, x of t is also going to stay in the same place across all time. So I'm just going to leave the t subscript off the x, plus a w recurrent, excuse me, f of x, plus w in u plus b. And I'm going to now call this function q of x. And what I want to then do is solve for states x such that q of x is equal to 0. All right. The way that we do that is we just formulate this as an optimization problem. So what we're going to do is we're going to write down a term 1/2 norm of q of x squared. And because I've now squared it, we know that this value achieves a minimum of 0, and it achieves a minimum of 0 when we are at a fixed point, when this expression is equal to 0. So if we minimize this expression over x, and we're able to find a place where then q of x, if we minimize this over x, then our optimizer will choose an x to make q of x as small as possible. And then if q of x squared goes to 0, then we know that we found a fixed point. And as Brandon will show you, PyTorch will give you libraries that automatically compute gradients and take optimizer steps. So you can just use your favorite optimizer here. You never have to, you could compute these gradients. It would probably take 30 minutes to an hour of sitting down and doing your calculus correctly. But you could also just, again, ask PyTorch to automatically differentiate this for you and then find the x that minimize it. All right, so I'm over time, so I'll just leave it at that. And the last part of the notebook that Brandon will walk you through will go over finding fixed points of the recurrent neural networks. I'm happy to take any questions on any part of this. Yeah.
So how do we relate this identifying fixed points towards the training of RNN, or is it solely independently?
The question is, how do we relate the fixed points to the training of the RNN? So the training of the RNN happens independently. It's done entirely from the supervised data. And then for that trained recurrent neural network, given its parameters w recurrent and w in, from there, we could compute the fixed points, the x that make this 0. So the fixed points are a consequence of the parameters which are learned through the training process. Question?
The minus xt term that you have here is the low pass filter property of the neuron, right?
Yes.
But isn't that describing a spiked neuron? So is your RNN more like a spiked neuron model, or?
Oh, great. So the question is, usually in spiking neurons, there's a low pass filter term as well. Is this recurrent neural network describing a spiking neural network? It is not. So this is a low pass term on the rates of the network. And it doesn't implement a spiking neural network, which you could do. It's a bit more challenging, but this low pass filter term is just a low pass filter on the actual rates. Okay, any other questions?
If not,
All right, thank you.